What I was demonstrating was the law of conservation of angular momentum. Now, that law says that the angular momentum of a system remains constant unless the system is acted upon by net external torque. Now, angular momentum is the product of an object's rotational inertia and its angular velocity. What I was doing by moving these masses in and out was changing the rotational inertia of my body. With the masses out, a fair amount of mass was distributed far from the axis of rotation, which was the vertical line passing through the center of my body and right through the stool. When I brought the masses in, I decreased the rotational inertia. Now, the angular momentum is the product of the rotational inertia and the angular velocity, and that remains constant as long as we don't have a net external torque. So at the beginning, I had a large rotational inertia and a relatively small angular velocity. When I pulled my arms in, my rotational inertia went way down and my angular velocity went way up in order to keep the product of the two a constant. Now let's look at this again with me holding two masses in each hand. This is going to give me a greater change in rotational inertia. There you can see that the changes in my angular velocity were greater because of the greater change in rotational inertia. Now, we've been saying that the law of conservation of angular momentum applies as long as no net external torque acts. In fact, there is a net external torque on the system. You can see because as the stool rotates, it will slow down because there's friction, which is exerting a torque on the axle. But this is small enough that you can still see the changes in angular velocity that are affected by the changes in rotational inertia. This is an effect that is used to good advantage by ice skaters in the high velocity spins that they achieve. They start their spin fairly slowly, but then they bring their arms and legs in very tightly, and that makes them spin at a very high rate.